In this video, we're going to be looking at 3 more examples of using the limit comparison test. So for our first example, we have the sum from n equals 1 to infinity of the square root of n to the 4th plus 1 over n cubed plus n squared. So I notice that I do have all positive terms here because I am dealing with just sums of powers of n. And now I want to think about what I could compare this to. Even though I do have a root here, this is still essentially like some sort of powers of n over powers of n, so we are thinking about using a comparison test because this is maybe similar to some kind of p series that'll be the sum of 1 over n to the p. So how are we going to think about what p series to compare this to? So we know our first step is to choose the comparison series. So we're going to choose our sum of bn. And in this case here, I'm going to sort of ignore the 1 when I'm thinking about picking my comparison series here and say that the numerator here is essentially like n squared. Okay, we know that, of course, the square root of n to the 4th plus 1 does not equal n squared. It also doesn't equal n squared plus 1, but it would behave kind of like n squared. And for the numerator, the highest power is that n cubed. Okay, so we're going to think about doing a comparison to the sum of 1 over n. Okay, so our next step is to determine the convergence or divergence of our comparison series. So we see that the sum from n equals 1 to infinity of 1 over n diverges by the p-series test. Since p equals 1 is less than or equal to 1. Remember, we also had a specific name for this series when p equals 1. So if you wanted, just to give you an alternate explanation here, you could say since it's the harmonic series, because the harmonic series, which is specifically the p series with p equals 1, is known to diverge. Okay, so you have a choice there when you're dealing with the sum of 1 over n. You can either say it diverges because it's the harmonic series, or it diverges by the p-series test, since p equals 1 is less than or equal to 1. Okay, now we're going to have the limit work step for the limit comparison test. Okay, so our plan here was to use the limit comparison test. So that means I need to find the limit as n goes to infinity of an over bn. Okay, that's the terms of the original series divided by the terms of the comparison series. So notice that our bn's are 1 over n, and the an's are the square root of n to the 4th plus 1 all over n cubed plus n squared. Okay, so I have my limit as n goes to infinity of the square root of n to the 4th plus 1 over n cubed plus n squared, and this is divided by 1 over n, so I'm going to say times n over 1. Okay, so now I have to think about the algebra that's going to be necessary to deal with this particular limit. Okay, so we can simplify this a little bit. I notice that I have n cubed plus n squared here in the denominator. If I rewrote that denominator as n times n squared plus n, okay, times n over 1, I'd see that would cancel a little bit. So I'm dealing with this limit as n goes to infinity of the square root of n to the 4th plus 1 all over n squared plus n. Okay, so when we're dealing with a limit as n goes to infinity, or previously with a limit as x goes to infinity when we were working with functions in Calc 1, and we have this root, we have a couple ways that we can do this. We can think about the technique of dividing by the highest power that we have in the denominator, but we're going to have to do a little bit of an extra step next in order to deal with simplifying this n to the 4th plus 1, which is under this root. So we're using that technique, dividing by the highest power of n in the denominator, that we often use for limits at infinity. But now in this second step, because I want to be able to bring that n squared somehow under my square root, I need to rewrite that n squared as the square root of n to the fourth. Okay, so n squared equals the square root of n to the fourth as long as we're dealing with some positive values here, which we are. So this is all over 1 plus 1 over n. Okay, so what does that numerator become here? Well, when I have the square root of something over the square root of something else, that could become the square root of that whole quotient. So I've got the square root of n to the fourth plus 1 over n to the fourth. So having that n to the fourth under the square root allows me to bring n to the fourth under the whole root. Okay, and this is all over 1 plus 1 over n. Okay, so notice that these limits can sometimes involve a little bit of algebra. When I divide my n to the fourth and my 1 each by n to the fourth, I have the square root of 1 plus 1 over n to the fourth. And then this is 1 over 1 plus 1 over n. Okay, so we see that 1 over n to the fourth is going to 0 as n goes to infinity. 1 over n is going to 0. So this limit is going to be 1. And we notice that 1 is a positive finite value. Okay, that was one of the requirements from our limit comparison test. We could only get a conclusion about the two series behaving in the same way as if that limit falls between 0 and infinity. If this limit had come out to 0, or if this limit had come out to infinity, we wouldn't be able to draw a conclusion. It would mean we'd have to do a different test. Okay, so step 4. Now we can say by 2 and 3, okay, because the sum of 1 over n diverges, and because our limit as n goes to infinity of a n over bn is 1, then our original series here must also diverge. So our sum from n equals 1 to infinity of the square root of n to the fourth plus 1 all over n cubed plus n squared diverges by the limit comparison test. Okay. So the comparison tests are really quite nice to use. You see something that looks kind of like a p-series, sometimes kind of like a geometric series, and we proceed through these steps and we can nicely show that our series has that same behavior. Okay, so let's look at a couple more varieties of examples. So here I have this sum from n equals 1 to infinity of tangent of 1 over n. So because I have this tangent function, it doesn't immediately maybe look to you like a p-series, but I do have a p-series or some sort of 1 over n to the p terms involved within the terms that I have for my given series. Excuse me, I have this sum of tangent of 1 over n. Maybe I want to try to do some kind of comparison to 1 over n here. To the sum of 1 over n. But first let's make sure that we have positive terms, because we know that the tangent function itself is not always positive. So is tangent of 1 over n always positive? Well, notice that for n greater than or equal to 1 over n is certainly always going to be positive, and it's also always going to be less than or equal to 1. Okay, as n gets bigger and bigger, you have some fractions here. Those are always going to be smaller than 1 and equal to 1 when n is 1. Notice that 1 would be less than pi over 2. So when we're talking about what kind of angle 1 over n is, it's an angle that would occur in the first quadrant. Okay, remember pi is 3.14, so pi 3.14 divided by 2, this is like 1.57. Okay, so pi over 2 is definitely bigger than what those 1 over n type angles would be. Okay, so this means tangent of 1 over n will be positive for n greater than or equal to 1, because I'm taking tangent of an angle in the first quadrant. Tangent in the first quadrant is positive. Okay, so we do have positive terms. So now we want to go ahead and choose the comparison series. And we're going to choose the sum of bn equals the sum of 1 over n. So actually making the same choice that we made in the previous example. And we know that this diverges okay, and I'll just go with diverges by p-series test, since p equals 1 is less than or equal to 1. Okay, so now we're going to need the limit work. Oops. So I kind of combine these steps. We chose it, and then we're also saying that that series diverges by the p-series test. Okay, so what about our limit work here? Well, I'm going to need to do the limit as n goes to infinity of an over bn. Remember, our an's are tangent of 1 over n, and the bn's are 1 over n. So I'm going to have this limit as n goes to infinity of tangent of 1 over n over 1 over n. Okay, so we notice that as n goes to infinity, 1 over n is going to 0. And I know that tangent of 0 is 0. So this is some kind of 0 over 0 indeterminate form. Okay. Now I know I can't use L'Hopital's rule right away on this limit because my n is understood to be integers, and L'Hopital's rule requires me to take some derivatives. So I'm going to write down the related function here of tangent of 1 over x over 1 over x, and look at the limit as x goes to infinity of tangent of 1 over x over 1 over x. And then we can apply our L'Hopital's rule. So we can say we have the limit as x goes to infinity here. The derivative of tangent of 1 over x is secant squared of 1 over x times the derivative of 1 over x, which is negative 1 over x squared, divided by the derivative of 1 over x, which is negative 1 over x squared. So we're looking at the limit as x goes to infinity of secant squared of 1 over x, since these negative 1 over x squareds cancel. So notice that, again, 1 over x is going to 0, and we know that secant squared of 0 is like 1 over cosine squared of 0, and cosine of 0 is 1. So this does come out to be 1. You'll notice that we get 1 a lot of the times for our limit, but the limit does not have to be 1. It will be 1 if your the thing that you chose is growing very much the same way as your original terms. But like we saw in our first example where we could have chosen, we were doing some kind of comparison to the sum of 1 over 2n squared, but we saw we could also just do a comparison to the sum of 1 over n squared. And we ended up with a half for our limit instead of 1, and that was perfectly fine as well. Okay, so lots of times you will get 1, but you do not have to get 1 as the limit for the test to work. Okay, but we notice that 1 does meet the conditions for this test, that it's a positive finite value. And so now I can go to my conclusion and say, okay, so by my work here in 2 and 3, because the sum of my 1 over n diverges, and because my limit of an over bn is going to 1, then my original series, this tangent of 1 over n from n equals 1 to infinity, diverges by the limit comparison test. Okay, because I compared it to the sum of 1 over n, showed that those terms were growing at the same rate, so this sum must also diverge. Okay, so let's look at one more example. In all the examples that we've looked at so far, we've compared to a p-series, but I also mentioned that sometimes we might want to compare to a geometric series, and we'll see an example of that in this last example. So here I have the sum from n equals 1 to infinity of n plus 4 to the n over n plus 6 to the n. So I first asked myself, do I in fact have positive terms? And the answer is yes. Okay, I'm just adding things. 4 to the n and 6 to the n will always be positive. I'm adding n's to those. So I need to think about choosing my comparison series and thinking about how I want to choose that. Okay. So when we're thinking about choosing the comparison series, if you have both a combination of n to some power and a number to a power, the number to a power grows faster than the n to a power. So a number to a power is some sort of exponential, okay? And an exponential function always grows faster than a power function into just a number. So the most important term in the numerator here is 4 to the n, and the most important term in the denominator here is 6 to the n. Remember when we just had powers of n over powers of n, we picked the highest power of n in the numerator over the highest power of n in the denominator? Now this exponential thing kind of beats the highest power of n. So I'm going to choose to compare this to the sum from n equals 1 to infinity of 4 to the n over 6 to the n. And notice that that means that's 4 over 6 to the n, or 2/3 to the n. So we see that is some sort of geometric series. Okay, so notice that the sum from n equals 1 to infinity of 2/3 to the n, okay, would equal 2/3 plus 4/9 plus 8 over 27, etc. So this is a geometric series with a equals 2/3 and r also equals 2/3. So using our geometric series test here, we can say that this series converges by the geometric series test, so we can use that abbreviation, since the absolute value of r equals 2/3 is less than 1. Okay, so we've chosen our comparison series, shown that that series converges with an explanation here. So now we can go ahead and do that limit step. So I'm going to do the limit as n goes to infinity of an over bn. Notice that our an's are exactly what we have in our original series to start with, n plus 4 to the n over n plus 6 to the n. And I need to divide this by my b to the n, excuse me, by my bn's. Here, I think it will be helpful to use the unsimplified form of our bn's. So we'll do divided by 4 to the n over 6 to the n, or times 6 to the n over 4 to the n. Okay, so what does this give us? We have the limit as n goes to infinity here of 6 to the n times n plus 4 to the n over 4 to the n times n plus 6 to the n. Okay, so if we multiplied the 6 to the n through, if we distributed, let me just write the distributed form here so we can see what our terms look like. I have n 6 to the n plus 4 to the n 6 to the n, and n 4 to the n plus 4 to the n 6 to the n. Okay, so with our limits as n goes to infinity, when I had powers of n over powers of n, to see what was what that limit was going to, we often divided by the highest power of n in the denominator. Here, I want to divide by sort of the term that's growing the most, and that's that product of these two exponentials. So I'm going to divide the numerator and denominator by 4 to the n 6 to the n. And see where that gets us. Okay, so we have our limit as n goes to infinity. N 6 to the n divided by 4 to the n 6 to the n. The 6 to the n's cancel, so I have n over 4 to the n, and then that's plus 1. N 4 to the n over 4 to the n 6 to the n. The 4 to the n's cancel. This is n over 6 to the n, and then I have plus 1. So then the question is, what's going on with our n over 4 to the n and our n over 6 to the n? Okay, so before we finish that, I want to kind of do an aside here and say, if f of x equals x over a to the x, so just kind of do something more general, because the n over 4 to the n and the n over the 6 to the n are the same form. You have some variable here over a number to a variable. Okay, we could say, well, in general, what's the limit as x goes to infinity of x over a to the x? Okay, well, that would be some sort of infinity over infinity. I'm just going to label that infinity over infinity, and then we can apply L'Hopital's rule to that. So I can say this is the limit as x goes to infinity of 1 over, and then we have to remember our general rule for the derivative of a to the x. Okay, well, that derivative rule is a to the x times log a. Okay, remember the derivative of e to the x is just e to the x, but in general, if you have some other base there, the derivative would be that exponential and then times log of the base. Notice that for the exponential function, this would be e to the x times log e, and log e is known to be 1. Okay, so now notice I have 1 divided by this a to the x log a. As x goes to infinity, this denominator is getting very big, so this limit will be 0. Okay, so that means that each of these two pieces here are going to 0, so this limit is 1. Okay, And we observe again that that limit is a finite positive value. Okay, so we can say for our conclusion here, trying to figure out where I might want to write the conclusion. Let me just clear out some space over here. So we can say, so by 2 and 3, okay, we've shown that our comparison series converges, and we did this limit to show that the terms of our two series are growing in the same way. So our original series, the sum of n plus 4 to the n over n plus 6 to the n from n equals 1 to infinity, also converges by the limit comparison test. Okay, so please let me know if you have any questions on applying these comparison tests.